Good day, everyone. My name is Irfan Fazrin bin Irwan, and my matrix number is CE240195. Today, I'm excited to present my proposal for an independent solar PV system with integrated energy storage designed specially for residential use. Our core mission with this project is move beyond just installing panels and instead design a truly self-sufficient power supply. To achieve this, our presentation will focus on four key pillars. First, establishing a design that works independently of the grid. Second, conducting a rigorous load analysis to ensure the system is perfectly sized. Third, prioritizing safety through MCB and RCCB protection integration. And finally, evaluating whether this system makes sense from both an economic and environmental standpoint. Problem-solving analytical. Before looking at the solution, we must understand the challenges we are addressing. Currently, homeowners facing a double-edged sword, a heavy dependence on non-renewable energy and the burden of rising electricity costs. For, from a technical perspective, the biggest risk in solar design is guessing. If you're under design, the resident face power shortage and frustration. If we over-design, the initial capital costs become a barrier to entry. So our goal is to solve the operational gap, ensuring that even during periods of low sunlight, the home remains powered through reliable storage while keeping the overall system simple enough for residential maintenance. And this is our house and layout and load analysis. To move from theory to practice, we've analyzed the specific house layout. As you can see from the floor plan and the accompanying symbol schedule, we're looking at a comprehensive residential setup. Key items in our load profile include climate control. We have three conditioning units, which is represent our largest peak load challenge. And daily essentials that it makes of 12 of wave switches, lamps, and socket outlet for airplanes. And other than that, specialized slots. We are account for high draw items like a water heater, electric cookers, as well as entertainment via the televisions. By mapping the symbols from the ceiling fans to the distribution board, this is DB that located to the near entrance, we can now calculate the total connected load. This allows us to size our battery bank and PV array with precision, ensuring the system can handle the morning coffee and afternoon heat in the individual light without interruption. And that's all for me. Thank you.
Hello and hi everyone. My name is Garrett Ivanhoe and my matrix number is DE240164. So today I will present about the load calculation with energy consumption. So on the left side, this is our table for our equipment. So the first one is downlight lamp. The quantity is 9 and it produces 12 watt for each of it. And the total power is 108. Consumed per month is 160 and the power consumption is 17.28 kilowatt hour. For the globe lamp, the quantity is 15 watt, and the total power is 15 and consumed per month is around 150 hours, and the power consumption is 2.25. For the pendant lamp, the quantity is 3, the watt is 15, and the total power is 45. Consumed per month hours is 120, and the power consumption is 5.4 kilowatt hour. Next is chandelier lamp. The quantity is 1 and the watt is 250 and total power is 250 watt. Consumed per month is 50 hours and power consumption is 12.5. Next is air conditioner 1.5 horsepower. So the quantity is 3, watt is 1119 and total power is 3357 and consumed per month hours is 100 hours and power consumption is 335.7. Next is ceiling fan. The quantity is 1, watt is 70 and the total power is 70. Consumed per month is 280 hours and the power consumption is 19.60. Next is wall fan. The quantity is 1, the watt is 65 and so the total power is 65. and consumed per month is 100 hours, and power consumption is 6.5 kilowatt hour. Next is exhaust fan. The quantity is 1, watt is 45, so total power is 45 watt, and consumed per month is 80 hours, and the power consumption is 3.6 kilowatt hour. Next is television. Quantity is 1, so the total power is 130. Consumed per month is around 100 hours, and the power consumption is 13 kilowatt hour. So next, water heater. Quantity is 1, total power is 3200. Consumed per month is 25 hours, and power consumption is 80 kilowatt hour. So next is washing machine. The quantity is 1, total power is 380, and consumed per month is 40 hours, and power consumption is 15.2 kilowatt hour. Next is oven. Quantity is 1, so the total power is 1400 watt. Consumed per month is 45 hours, and power consumption is 63 kilowatt hour. So the last one is refrigerator. Quantity is 1, so the total power is 300. Consumed per month is 720 hours, and the power consumption is 216 kilowatt hour. So for the total power consumption of this house is 790.03 kilowatt hour. So next on the right side is the average daily consumption, which is average monthly consumption divided by days in a month. So assuming 30 days in a month, so daily average daily consumption is 790.03 kilowatt hour. So divide by 30. So average daily consumption is 26.33 kilowatt hour per day. And next, so this is the total current monthly bill by TNB. So total current monthly bill by TNB. So the first one is average monthly consumption is 790.03 kilowatt hour. So second, the current bill by TNB for Malaysia TNB, typical residential rate are typed as follows. So 0 to 200 kilowatt hour, RM 0.218 per kilowatt hour. For 201 to 300 kilowatt hour, RM 0.334 per kilowatt hour. Next, 301 to 600 kilowatt hour, RM 0.516 per kilowatt hour. Next, 601 to 900 kilowatt hour, so which is RM 0.546 per kilowatt hour, and the last one is above 900 kilowatt hour, which is RM 0.5 per kilowatt hour. So this is our calculation for the first 200 kilowatt hour. So the cost is equal to 200 times by 0.218, so equal to RM 43 ringgit and 60 cent. So next, 100 kilowatt hour, which is 201 to 300 kilowatt hour. Cost is equal to 100 times by 0.334 is equal to RM 33 ringgit and 40 cent. So the third one is 300 kilowatt hour, which is 301 to 600 kilowatt hour. So the cost is equal to 300 times by 0.516. So it's equal to RM 154.80. So next is 300 kilowatt hour for 600 kilowatt hour, which is 601 to 900 kilowatt hour. So the cost is equal to 190.03 times by 0.546, is equal to RM 103.76. So the total current bill by TNB, we add it all, and the answer is RM 335 ringgit and 56 cent. So next, as at percent service tax. So service tax equal to 0.08 times by RM 335.56, which is equal to RM 26 ringgit and 84. So lastly, the total current bill is equal to RM 335.56 plus RM 26.84 is equal to RM 362 ringgit and 40 cent.
Next, I will explain the manual sizing calculation for the solar PV system. First, we determine the required PV power based on the daily energy consumption. From our load calculation, the total daily energy consumption is 26.33 kWh per day. For Malaysia, we assume the average sun peak hours is around 5 hours per day. To consider system losses, such as inverter loss, temperature effect, and wiring loss, we apply an efficiency factor of 1.5. So the PV power is calculated using the following formula. PV power equals daily energy consumption divided by some peak hours multiplied by the efficiency factor. By substituting the values, 26.33 divided by 5 multiplied by 1.5, we obtain a required PV system size of approximately 7.9 kilowatts. Next, we calculate the number of PV panels needed. The selected solar panels has a rated power of 550 watts, which is 0.55 kilowatts. The number of panels is calculated by dividing the required PV power by the panel rated power. So 7.9 divided by 0.55 give 14.36 panels. Since we cannot install a fraction of a panel, the value is rounded up to 15 panels. So that concludes the manual sizing calculation for the solar PV system. Next, I will explain the battery bank sizing for the solar PV system. First, the battery bank is designed to store enough energy to supply the daily load when there is no sunlight, especially during night time. The battery bank capacity is calculated using this formula. Battery capacity equal daily energy consumption divided by the product of depth of discharge, efficiency, and system voltage. From our previous calculation, the daily energy consumption is 26.33 kilowatt-hour. We select a depth of discharge of 0.8, which means only 80% of the battery capacity is used to improve battery lifespan. An efficiency of 0.9 is applied to account for losses in the battery system. The selected system voltage is 48 volts, which is commonly used for residential solar system. By substituting all the values, the required battery bank capacity is approximately 36.57 kilowatt-hour. Next, the battery capacity is converted from kilowatt-hour to ampere-hour, since battery ratings are usually given in the ampere-hour. Using the conversion, we divide 36.57 kilowatt-hour by the system voltage of 48 volts, which gives a battery capacity of approximately 761.9 ampere-hour. After that, we determine the number of battery strings required. Each battery has a rated capacity of 100 ampere-hour. The number of strings is calculated by dividing the total battery bank capacity by the battery rating. 761.9 divided by 100 give 7.62 strings. Since we cannot install a fraction of a string, the value is rounded up to 8 battery strings. So that concludes the battery bank sizing and number of strings calculation.
Next is the power generation that we use for our project, and that is solar system. We can see from this picture is that we use solar panels to receive sunlight, and from the sunlight we will transfer it into a DC power and will convert to AC, and it will go through a few another process, and then it will generate electricity for the household. So why we choose solar system? Because it is much more efficient. Next is protection device recommendation, and that is MCCB and RCCB. The model that we chose MCCB for our project is ABB A1C125. It is rated between 40 to 63 amps and comes in 2 or 3 pole options, depending on whether the system is single phase or 3 phase. Its main function is to protect the system from overload and short circuits using thermal and magnetic trippings. This makes it ideal for protecting the main supply and inverter output. Okay, next, the model for SSGB is RS Pro 63M model with a sensitivity of 30 milliamps. It is a two-pole device that protects users from electric shock by detecting earth leakage current. This device is essential for life safety. So we can see that MCCB provides equipment protection, and while RCCB is ensures human safety.
So the comparison between conventional grid supply and solar PV system. And for the conventional grid supply, electricity mainly generated from fossil fuel. These resources are finite and require intensive extraction methods like mining and drilling that will harm the environment. And then high carbon dioxide emission that will trap heat in the atmosphere and leading to global warming and climate change. And lastly is greater negative impact on the environment. Beyond CO2, conventional power plants often contribute to air pollution such as sulfur dioxide, nitrogen oxide, will consume massive amount of water for cooling and can lead to habitat destruction during resources extraction and plant construction. Next is the solar PV system. First is uses renewable solar energy, which is sunlight, is an inexhaustible resources. This utilizing solar energy reduce our dependence on finite, depleting natural resources. Next is produce minimal CO2 emission during operation. This will the actual generation of electricity by a PV system produce no noise, no air pollution, and zero CO2 emission. Lastly is reduce carbon footprint and environment impact that will generate electricity on site from a clean sources. A user significantly reduce their carbon footprint, which is the amount of greenhouse gases generate by their action. Okay, for the conclusion for this project is we successfully designed an off-grid solar energy system for a single-story residential house. And then the total connected load is 9,365 watt with maximum demand of 3.76 kilo VA. And then we propose system is 7.9 kilowatt PV system, 15 solar panels, and 761.9 AH battery bank. And then we eliminate monthly TNB bills of approximately Rm 362 ringgit and 40 cents. And we produce environmentally friendly solution with reduced carbon emission. Lastly, we make a safe and reliable operation ensure using MCCB and RCCB protection device. That's all from us, and thank you.